Welcome to the deep dive. Now, if you follow the clean energy transition, you definitely know the core challenge.
Yeah.
How do you actually integrate massive amounts of solar and winds, the intermittent stuff? How do you do that without just flooding the grid when the sun's shining or the wind's blowing?
Yeah, it's the big one.
And the technical answer, well, it often points toward power to gas, or PTG. Taking that renewable electricity, converting it into fuels you can store, like hydrogen or synthetic methane. But look, for years, the question wasn't really if it worked technically, it was, could it ever actually be profitable? Profitable enough to move beyond just demos and, become a real commercial thing.
Right. Just making gas wasn't cutting it financially.
So our mission today is kind of a shortcut to understanding how that financial side got cracked. We're diving into one specific, very detailed study, a study that didn't just talk about viability, it built a model that showed a path.
That's exactly right. We're looking at an older paper, yes, but a really foundational one from 2015. It's titled Power to Gas as an Emerging Profitable Business Through Creating an Integrated Value Chain. And what this source showed was that let's say, the typical approach is that building a plant, selling the gas, well, it simply doesn't work financially. Not back then, anyway. The paper basically established that real financial success depends entirely on what they called the integrated value chain approach. You have to very deliberately combine your inputs, maximize all your output products, and crucially, make money from related services, all in the most beneficial way.
Okay, let's unpack that a bit. Integrated value chain.
Yeah.
So we're not just talking about selling the methane at the end of the pipe. It's about stacking different revenue streams together. Is that it?
Exactly. You need to think of PTG less like just a gas factory and more like maybe a mini chemical complex and a utility service provider all rolled into one. At its core, PTG uses electrolysis, right? Powered by renewables, splits water into hydrogen, H2, and oxygen, O2. That H2 can be used directly, or you combine it with a carbon source like CO2 through a process called methanation. And that gives you synthetic natural gas, or bio-SNG.
And that gas has tons of uses. Seasonal storage, fuel for trucks or ships, feedstock for chemicals.
Yeah, the applications are broad, but the complexity and where the profit potential lies, according to this study, is in managing all the resource flows. They map this out really clearly. Your main inputs are electricity, water, and CO2. But to make money, your outputs need to be hydrogen or methane, plus the saleable byproducts, oxygen and heat.
So if you just vent the oxygen or waste the heat.
You're basically throwing money away. Millions, potentially.
Which really highlights why profitability was, well, so tricky for so long.
Yeah.
Getting past the demo stage meant optimizing everything, finding sometimes niche, high-value markets for every single thing coming out of that plant.
And being incredibly sensitive to prices. The study pointed out this dizzying array of external factors. You're balancing the cost of electricity, which fluctuates wildly, against selling prices for H2, CH4, and O2, and heat. Plus, you need to consider the cost and type of your CO2. Is it fossil-based, or is it cheaper, sustainable bio-CO2? And then maybe the most critical piece they identified, the price you can get for grid services.
Wow, okay. It's like threading a really complex financial needle. So to actually prove this integrated value chain idea, they didn't just model some generic plant. They looked at a specific real-world case, right? Integrating PTG into a pulp mill in Finland. Why there?
This is where the integrated value chain concept really clicks. It's quite clever. They chose UPM's Kaukas mill. It's a big one. It makes about 0.74 million tons of air-dry pulp per year. And this specific location, this mill, it solved like 4 huge problems that would probably bankrupt a standalone PTG plant.
Okay, so what was the first big synergy?
Yeah.
Most critical one.
Getting the carbon. Making synthetic methane needs CO2, right? And for it to be green methane, that CO2 needs to be sustainable. Well, a pulp mill like this is a massive, consistent source of sustainable wood-based bio-CO2. It's just part of their process. About half the carbon in the wood they pulp ends up as CO2 from their recovery boiler.
Oh, good.
This study estimated a mill making 1 million tons a year produces enough bio-CO2 to generate something like 11 terawatt-hours thermal of synthetic methane annually. That's a huge, essentially carbon-neutral feedstock supply, secured cheaply right on site.
Right, okay. So problem 1, clean, cheap CO2 solved. What was next?
Problem 2. What about the oxygen? Remember, electrolysis splits water into H2 and O2.
Yeah, the byproduct.
Exactly. Well, the pulp mill needs oxygen for its own process, about 20 kilos per ton of pulp. So the PTG plant's waste O2 can directly replace the mill's existing oxygen supply.
Ah, brilliant. So you turn a byproduct you might have struggled to sell into a guaranteed internal sale, or at least a cost saving for the mill.
Precisely. That's the integration working. And then there are the logistics.
All right, what about those?
Just made sense. The mill already has deionized water, which you need for efficient electrolysis. It's already hooked up to the high voltage 110 kV grid for power, and it's connected to the natural gas pipeline to send the final S&G out.
So the infrastructure is basically already there. Cuts down costs massively.
Hugely. And then the final products, the H2 and the SNG, how did they fit those into the local picture?
Yeah, where did they go?
Okay, so the hydrogen produced, the H2, gets piped to a nearby biodiesel plant. This plant makes something called HVO, hydrogen-treated vegetable oils. Normally, that plant would get its hydrogen from steam-reformed natural gas, which is fossil-based, but using the renewable H2 from the PTG plant, that dramatically bumps up the economic value and the green credentials, the renewable energy content of their final biodiesel, makes it much more valuable.
Okay, so the H2 goes to a high-value use. What about the methane, the SNG?
The bio-SNG, the synthetic methane, that gets sold into the premium mobility market, so for transport fuel, another high-value offtake.
So you've got this, like, perfectly closed loop. Cheap inputs, shared infrastructure, byproducts sold internally, high-value markets for the main products. It sounds ideal. And yet, despite all that synergy, the study found that if you just ran the plant flat out, baseload, it still didn't make money. Why not?
This is probably the absolute core finding, the financial pivot. They modeled two main plant designs. Both had the same electrolysis capacity, 9.6 megawatts electric, and they calculated annualized profit and, importantly, return on equity, ROE. So Case A was designed for full methanation, turning all the H2 into methane, and it just ran continuously, baseload operation. Case B, though, used only partial methanation, just 1.2 megawatts worth, but critically, it was designed to operate flexibly. It could offer significant power capacity, plus or minus 4.8 megawatts, back to the grid as a balancing service.
And the punchline, the big reveal from this 2015 study, Case A, the one just making gas all the time, the baseload approach, could make a positive return, even with all that integration.
It failed financially, even though it actually required more capital up front, about 17.9 million euros in their model, compared to 15.5 million for Case B because of all the methanation equipment.
Why? Why did it fail?
Because running continuously meant it was buying electricity whenever it needed it, even when prices were high. And the revenue from just selling the gas couldn't cover those high fixed costs and the high variable energy costs.
That's such a key point, isn't it? PTG plants are expensive, so you think you need high utilization, but high utilization can mean buying really expensive power, which kills your profit margin.
Exactly that paradox. But Case B, the flexible one, it achieved an 11.0% return on equity, and that's assuming standard project financing, like 80% debt.
11% ROE.
Right.
Even though it had lower capital costs and produced less gas overall.
Correct, because the money wasn't just coming from the gas.
Okay, this is where it gets really fascinating. The income source that flipped Case B from red to black? Grid services.
That was the game changer. Grid services accounted for a massive 40% of Case B's total income. 40%. And the reason this works is that modern electrolyzers, even back then, have incredibly fast ramp rates. They've mentioned up to 20% of capacity change per second. That speed is exactly what grid operators pay premium prices for balancing services.
So we're talking about things like frequency containment reserve, FCRN, the stuff that keeps the grid stable second by second. The electrolyzer can quickly ramp power use up or down to help balance things out.
Spot on. And the study showed just how much more valuable that is. The hourly spot market for FCRN in Finland back in 2013 averaged 36.3 euros per megawatt. Compare that to just 14.36 euros per megawatt if you signed up for an annual contract.
So by operating flexibly, playing that spot market, the plant was getting paid a huge premium just for being ready to adjust its power consumption, not just for making gas.
Exactly. It's a service payment as much as a product payment.
And we can't forget the oxygen, right? Even with grid services bringing in 40%. That O2 sale to the pulp mill was still vital.
Absolutely critical. The study called the O2 income indispensable. It accounted for somewhere between 16% and 23% of total sales revenue. It just reinforces the point. You have to maximize every part of that integrated value chain. No wasted streams.
Okay, so the takeaway there is that even with 2015 technology, if you integrated it perfectly and ran it flexibly, it could be financially viable. But the study didn't stop there, did it? They looked ahead, projected what could happen with industrial scaling and maybe some policy help.
Right. They modeled what they expected the tech and cost to look like by the end of the 2010s. They looked at two main improvements. First, what happens if capital costs drop by 50%, which is, plausible with industrial scale-up and learning effects.
Yeah.
They assumed about a 13% learning rate.
Meaning costs drop 13% every time cumulative production doubles. That's pretty standard for new tech. What did just that cost reduction do to the ROE for Case B?
Just the scaling, the 50% capex reduction, it pushed Case B's ROE up from that 11% to around 62%.
62%. Okay. And the second factor?
The second variable was adding some policy support. For instance, attaching an attractive biofuel certificate value to the synthetic gas produced. They used an example of, say, 50 euros per megawatt hour thermal.
Right. So let's put it all together. What happens if you get both the scaling cost reductions and that policy support? The numbers they projected are, well, they're kind of eye-watering. What did Case A, the previously unprofitable baseload plant, jump to?
Okay, so if you combine both improvements, the scaling and the certificates, Case A, the one focused purely on high methanation, suddenly hits a projected ROE of 106%.
106% return on equity. In Case B, the flexible grid services one.
Case B hits 76% ROE. Still fantastic, but interestingly, the high-volume gas production model becomes even more profitable under those future conditions.
A triple-digit return. I mean, that completely changes the conversation about PTG, doesn't it? It stops being just this thing we need for the grid and becomes a potentially massive investment opportunity.
It really does. And that level of projected profitability immediately shifts where you'd expect the biggest market opportunities to be. It moves the focus away from, say, large-scale seasonal electricity storage, which needs the plant maybe sitting idle for long periods, making returns tricky towards two much higher value, higher impact sectors.
Which are?
The transportation sector, which we said with the bio-SNG, and perhaps even bigger, the chemical industry.
Let's talk about the scale there. The chemical industry potential.
Yeah.
It's
yeah.
huge. Right?
Oh, it's absolutely enormous. Current global industrial hydrogen use is somewhere around 1,500 terawatt hours. That's using the lower heating value LHV, which is the useful energy you get out. And right now, most of that 1,500 TW of hydrogen is made using steam reforming of natural gas. Fossil gas.
Right.
So PTG offers a direct route to replace the natural gas feedstock used in that process with green hydrogen. If you replaced all of it, that's equivalent to displacing roughly 2,000 TW fossil methane use per year globally.
Wow, that's a massive existing market just waiting for a cost-effective green alternative.
And it's a market where there's already pressure and sometimes a premium for decarbonization.
So bringing it all together then, what's the core lesson for us today, looking back at this really insightful 2015 analysis?
I think the main takeaway, and it's still incredibly relevant, is this. For PTG to work financially, especially using commercially available tech today, you absolutely must leverage that full integrated value chain. You need partners, like that pulp mill, to solve your input sourcing and byproduct offtake problems. You have to design for flexibility to capture high-value grid service revenues. And you cannot afford to neglect the income from things like oxygen or heat. It's non-negotiable.
And the study's conclusion that investors could potentially start backing PTG projects purely on the financials because of that high potential ROE down the line, that's pretty stunning. So here's something to think about. If every new plant helps drive down the cost for the next one, that 13% learning rate they mentioned, how quickly could this shift? How fast can we go from these very clever, specific niche applications like the Finnish pulp mill to PTG starting to make real inroads into decarbonizing massive global sectors like chemicals, especially if those 100% plus returns are genuinely achievable? That pace feels like a critical factor in the whole energy transition. We were taking a deep dive into the findings of power to gas as an emerging profitable business through creating an integrated value chain. Thanks for joining us.